Hey everyone. As we've been talking about gases, we've been thinking a lot about averages instead of thinking about individual particles. There's a really good reason for that. If we wanted to build a perfect model of a box of gas, we would need to model every single particle individually. We'd then have to model every single time that the particle bounced against the side of the box and every time it ran into another particle. We might be able to do this for a few particles, even maybe a few dozen if we had some good software. But as soon as the number of particles gets really big, this just becomes totally impossible. For that reason, we again just talk about averages. We don't really care what each of the individual particles is doing as long as we have a model that can tell us what the gas as a whole is doing. But of course, these particles are all doing their own individual thing. Some particles are moving faster than others, some are moving in one direction, some are moving in the other direction. Because of this, we want to spend a little more time thinking about this sort of averaging thing. So let's introduce two ideas, the idea of a microstate and the idea of a macrostate. Now, let's start by thinking about what a state is. In the context of a gas, a state is just a measurement of certain properties at a particular point in time. For example, if I told you the pressure and the volume and the temperature of a gas, that's a statement about what the state of the gas is. So what is a microstate and what is a macrostate? Well, a macrostate is just really a state as we've thought about it before. It's a combination of these sort of larger picture things that we can measure about a gas: pressure, volume, temperature, number of moles, and so on. But as we've said, this state sort of hides a lot of information. The individual particles are all doing a particular thing, and it's the collection of all those particles together that gives us the macrostate. The microstate is just a description of how every single individual particle in the system is behaving. It would tell us exactly where each particle is, which direction it's going, how fast, and so on. Now, as I sort of hinted at, you're never going to be asked to actually think about individual particles and how they're moving. And in fact, in physics, we don't ever do this either. We just sort of think about the statistics. So to understand why this is useful, let's go to a much simpler example, the case of rolling two six-sided dice. When you roll a six-sided dice, you're effectively picking a number between 1 and 6 at random. If you roll two six-sided dice, those dice will independently pick one number between 1 and 6. And then when you look at the dice together, you can add those two numbers up to then calculate a total value. You can think about the individual numbers of the dice as the microstate of the system. You can think of the total combined number as the macrostate. For example, you could roll a 3 and a 4. That is a specific microstate, and the macrostate would be 7 because 3 plus 4 is 7. But you could also roll a 5 and a 2, or a 6 and a 1. In that case, your macrostate would be the same. The total of the dice would still be 7, but your microstate would be different because, well, the dice individually have different numbers. Now, there's a really, really important thing that we have to understand about this, and that is each microstate of the dice, in other words, each individual pair of numbers, is equally likely. You are just as likely for dice 1 to have a 6 and dice 2 to have a 5 as you are for dice 1 to have a 3 and dice 2 to have a 4. But crucially, the macrostates are not equally probable. The reason is just that there are more ways of rolling one number combined than there is another number. For example, there are a ton of different ways that you can roll a 7 with two dice. You can roll a 1 and a 6, a 2 and a 5, a 3 and a 4, or flip it, 4, 3, 5, 2, 6, 1. But if you wanted to roll a 12, there's only one way to do that: roll two sixes. So if you roll two dice and each one is picking a number between 1 and 6 at random, then the probability that you end up with a 12 when you add the two dice together is much lower than the probability that you end up with a 7. We can actually calculate this explicitly. If you know the total number of possible microstates for a system, and you know the number of microstates that corresponds specifically to the macrostate that you want, then you can calculate the probability of that macrostate by just taking the number of microstates for the particular outcome that you want and dividing by the total number of microstates that the system can have. For example, let's go back to the dice case. There are 6 different ways to roll a 7 when you roll a die. It's 1 6, 2 5, 3 4, or 4 3, 5 2, 6 1. 6 possible outcomes. If you roll 2 dice, there are 36 total possible outcomes that you can get, 36 possible microstates. And so the probability of rolling a 7 when you roll 2 dice is just the number of microstates that will give you a 7, which is 6, divided by the total number of possible outcomes for the 2 dice, which is 36. And so the probability of rolling a 7 is 6 divided by 36, or 1/6. Compare this to the odds of rolling a 12. There's still 36 possible outcomes when you roll the dice, 36 possible microstates. But now only one of those microstates corresponds to the outcome that you want, a 12. And so the probability of rolling a 12 is just the total number of microstates that give you a 12, which is just 1, divided by the total number of possible microstates when you roll 2 dice, which is 36. And so your probability of getting a 12 is 1 out of 36. Now, 1 out of 36 may seem unlikely, but when you compare it to systems of large numbers of things, it's actually pretty likely. 1 in 36 is not 0, and so if you roll a dice a bunch of times, you will eventually see a 12. But let's think about a different system. What if we flipped a coin 100 times, and we wanted to make a prediction about how many heads we would get? Now, you might say that the most likely outcome is half and half. If it's a fair coin, then about half the time you're going to get a head, and about half the time you're going to get a tail. And so that's correct. The most likely outcome is that you get 50 heads and you get 50 tails. You would probably be really surprised if you flipped a coin 100 times and got heads every single time. You'd have good reason for being surprised. The odds of this are extremely, extremely low, but crucially not impossible. It is possible to flip a fair coin 100 times and get 100 heads. But it is so unlikely that you could do this every second for longer than the universe has existed, and you still would not be likely to end up with 100 heads. It's not like the case of rolling the dice. Even though getting a 12 is the least likely outcome, it's still fairly probable, and if you roll a dice enough times, you're probably going to get a 12. But again, for a much larger system, this is just not the case. The odds of flipping 100 heads in a row is basically 0. Not actually 0, but it might as well be 0 for how unlikely that it is. But another interesting thing, it's also fairly unlikely to get exactly 50 heads and 50 tails. If you flip the coin 100 times and you got 49 heads and 51 tails, you probably wouldn't conclude that the coin is somehow unbalanced. Things just happen, and sometimes you end up with 51 heads and 49 tails. But the farther away you get from exactly 50-50, the less likely this thing becomes. If you flipped 65 heads and 35 tails, you'd probably be a bit suspicious. This is much more likely than flipping 100 heads, but it's still pretty unlikely when you flip a coin 100 times. If you imagine repeating this experiment over and over again, you would probably get a range of the number of heads that you got. You'd probably get 50-50 the most, but you'd also get 49-51 sometimes, or 48-52, or 52-48. There's all these different outcomes that you could possibly get, and the actual numbers that you found would be somewhere in that range. So how does this connect to gases? Well, the properties of gases that we know how to measure can be thought of kind of like this. The particles in the gas are always bouncing around and changing their directions, changing their speeds, all that sorts of thing. Measuring something like the temperature of a gas is sort of like flipping 100 coins. If you run the experiment a bunch of times, you're going to see fluctuations. The temperature will be a little bit higher sometimes, a little bit lower sometimes. This is just because the temperature depends on the particular microstate that the gas is in. There's going to be some number, some temperature that's going to be the most likely outcome when you measure it. But this number can fluctuate up and down a little bit as the system moves between all the different kinds of microstates. But a really important thing happens as the number of particles gets very large. The range of outcomes that are likely gets really, really small. If you have a mole of gas and you measure the temperature a bunch of times, you will see little fluctuations. But that fluctuation is going to be extremely small, a fraction of a fraction of a fraction of a fraction of a degree. And so even though it's true that the temperature does not have a specific value, the fluctuation is small enough that we can pretend that it has a specific value and get the answers pretty much right. Now, you're not going to be given, say, a microstate and asked to calculate the temperature. That's way beyond what we have time to cover in this course. But it's really critical to understand that this is actually what's happening at a basic level. Particles are particles. They're real. They're actually in a position and moving in a direction. If we wanted a perfect model of a gas, we need to take all this into account, but we just can't. Now, again, there is a critical thing we need to be aware of. This statement that I made earlier in the video, that each microstate for a system is equally probable, is only true in a particular case. It's only true when the system is at equilibrium. Let's imagine I had a box of gas. The gas just fills up the entire box because, well, it's a gas. But the reason that this is the case is that there are so many microstates where the gas is evenly distributed throughout the box. It's not that there aren't microstates where all of the gas is on one side of the box. There are microstates like that, but there's just so few of them, it's like the case of flipping 100 heads in a row. Not impossible, but extremely unlikely. The gas in the box is an example of a system at equilibrium. The particles in the box are just being allowed to freely move. We're not interfering with them. But now let's imagine that we actually pushed all the particles over to one side through some way. Now the particles are all on one side of the box, which, as we said, is extremely unlikely. But nothing's broken here. We've actually interfered in the system and pushed it out of equilibrium. When we say that a system is in equilibrium, we just mean that it's been allowed to just do its own thing without any interference for a long amount of time. If we now remove whatever is causing the gas to remain on one side of the box, the gas will now just spread out naturally and fill up the entire box. Again, it does this because the number of microstates where the gas is evenly spread out throughout the box is just massively greater than the number of microstates where all of the particles are on one side of the box. Now, if you sat and watched this gas for trillions of years, would maybe all the particles in the gas randomly end up on one side of the box? Maybe, maybe not. You never really know. It's possible, but super unlikely. Now, in this course, we're not going to learn about how we can actually calculate probabilities for the various states that we might find a gas in. It can be done, but the math is really advanced and complicated and not super interesting. But we might ask you to calculate probabilities for much simpler systems. You'll actually see how to calculate real probabilities for this in DL. But again, the key thing to take away here is that gases are made up of particles, and the particles are always moving around and changing. This causes the gas to change some of its quantities all the time: pressure, temperature, volume, and so forth. But for very large numbers of particles, this change, this fluctuation, is very, very small compared to what the actual values are. So for example, if we're trying to calculate the thermal energy of the gas, it doesn't really matter that the temperature is fluctuating a bit because that fluctuation is just too small to really matter. Now, I've just said that we're not going to be asked to calculate these things explicitly for gases. So why have we introduced this? Well, we've introduced this because we want to look at an idea called entropy, and that's what we'll do in the next video. See you then.